Hello, everyone, and good afternoon. My name is Marika Reckler, and welcome to our AIRAH Technology Talk webinar session for today. Just before we get underway, I'd just like to start off by acknowledging the traditional custodians on the lands of which we all gather today, and pay my respects to their elders, past, present, and emerging. So today's technology talk is on sustainability improvement solutions for data centres, and it is presented to you today by Carrier. As always, if you do have any questions throughout the presentation, please type them into the Q&A box that's located just at the bottom of your screen, and then together with our presenter, we'll be able to go through as many questions as possible after the formal presentation. So I'd now like to introduce to you our presenter today, who is Michel Grabon, who is the global leader for data centres at Carrier. Michel is based in France and is also the head of advanced systems and the refrigerants team. So Michel, I'll pass things over to you now, and you can get the session underway for us. Thank you.
Thank you for hosting me, and it's really impressive for me when I'm thinking that I'm just in the opposite side of the earth, talking to you from France, and you folks who are sitting in Australia. It's a pleasure, and I'm really proud to be to have this opportunity to talk to you. It's difficult, in 1 hour to summarize everything which could be said about sustainability in data centers. So I will probably touch upon maybe 1 or 2 specific subject, mainly concentrated, on one of our new product, and explain you why we have done this, and put a little bit of context of application of this specific technology. You see the picture here in Australian situation. Okay. First of all, I will just use 1 or 2 slides to introduce myself. Like Barry have said, I'm a relatively old engineer with a lot of experience. More than 33 years, mainly in technology areas, with several different type of work which I've been doing. So I was working technology side. It means developing new refrigerants, new heat exchangers, new compressors, new fans, and you name it. Then I have spent a lot of time working on what we call product, but basically in developing new generation of chillers. So I'm sure that if you go across Australia, you can find some of the product which were developed by my teams. We call them 30RBs, 30XAs, some other products, 30GXs in previous generation. So I'm proud to say that there is a lot of product which actually I was a part of team developing those. And then last probably 10 years, I have switched more to what we call system. System is more than just, addition of several components, and we have realized that by smart system architecting and by working closer with customer, we actually can achieve much higher energy savings. And what actually drives me in all my work, since years, is basically sustainability, in the sense that I really understand thermodynamics, and I know that only engineers like us can have a solution which really works to reduce the impact we have on environment. So whatever waste we are generating, I always feel bad, and but we have to live in better environment, in terms of comfort and the technology. But we as engineers, we have to provide solution which has a minimum or less possible impact on environment. So everything I do goes in this direction. It's extremely important for my company. I will not make here the speech about engagement of Carrier. We call this ESG goals. It's not only about being green, but also of being a part of community, be a kind of infrastructure. And we as majority of large company, but it's particularly true for Carrier, and that's why I'm proud to be a part of this organization. It's taken really seriously into account. It's not only painting in green, whatever we do. whatever processes, whatever product development, whatever manufacturing processes, building new factories, everything we do has impact on environment, and Karian knows this very well, is tracking and trying to reduce. So I will not enter into the details, but generally speaking, we have a very, very aggressive goals to reduce our impact. And frankly speaking, even in the product I will talk today about, it was in 2006, I think I was in this time on charge of new refrigerant technology group, and we have introduced HFO 1234ZE as the first in the market. So we actually found this formulation, which was different from what car industry was using, and today it has become a kind of industry standard, and impact on environment is very, very low. So transition very quickly now to a little bit of technology and product. Today I will concentrate about one specific product, which we use always the strange names, but our brand name is 30XF. I'm not sure which of you knows already carry a product portfolio, but generally speaking, it's the product which it's a kind of specific one which integrates all new technology which Korea has designed last probably 3 to 5 years, but we have created a product which was especially designed for data center. So it's very, very new for us. I'm not sure if everybody else is doing so, but generally speaking, if you take Carrier products, chillers, heat pumps, and you name it, generally speaking, they are designed for very broad applications. So it can be applied in industry, in low temperature, high temperature. It can be applied, in air conditioning and different type of industries. This product is the only one I know of. Actually, is the second, but this one is very specifically designed for one type of customer, one type of application. And why we have done this, we have realized that recently, last 5 years, data center collocation, large data center has tendency to a kind of converge for the common design. They were, a lot of different architectures, a lot of different type of thermal approach to data center. And now more and more company, not all of them, but a lot of company are selecting the units or designing data center, which uses multiple, relatively large size air-cooled chillers. So you can see here, we can go up to around 2 megawatts, operating with very high living water temperature. So it's high for traditional air conditioning. Usually it's 30 return, 20 supply water temperature. And with ambient condition, which you can find in the globe everywhere. And usually we have specific options which are dedicated to the data center, which I would say integration or added value options. Customer wants to have as much as possible hardware and function be a part of chiller to avoid to reproduce, when they are building the new site, some of those construction and integration problems. So this specific chiller needs to take into account of the constraints of data center, different cheering, different redundancy, probably better than me, this specific market. But what I wanted to say, this specific chiller was designed for data center and was designed specifically for free cooling application. It's not only free cooling, but it can do free cooling. And when I was preparing talk for Australia, my first reaction was, that Australia is very, very hot country. Probably there is not too much free cooling opportunities there. I will talk a little bit about this, and you will be surprised by the results. So few things about the technology. You may say chiller is a chiller, but we have integrated in this specific product design some technical elements which make this product unique and very, very well deserved for data center. So just to mention some of them, you know, we have integrated what we call hydronic filter, you know, up front, or you can call it THDI filter, total harmonic distortion filter. Those products by definition, by nature, has variable speed compressor. So this is the latest compression technology. But when you apply a lot of variable speed compressor, then you can have, you know, impact on quality of power line. So you have to have specific filtration elements which allows you to reduce distortion, which may have influence on other elements in the same distribution network. We have a very sophisticated controls. Controls is not only human interface, which everything which is inside, you know, I will not talk much about this, but there is a lot of optimization algorithms. There is a lot of data which can be extracted from the chiller and provided to the customer, you know, including very accurate estimation of input power, cooling capacity, all elements, you know, which are necessary for prediction, early detection of any issues, and you name it. Very important option. I will not talk much about this. So only this in this slide I have this information. It's what we call ultra fast capacity recovery. So you may know the data center. They have very stringent rules about, you know, how quickly system has to be restarted after power failure or power line test. You know that usually in data center they have specific in-house power generators to back up the power in case external power is broken. So this transition between one power supplier and another power supplier goes through zero. So you need to stop power supply, then restart generator and connect again to your data center. And in the same time, data center is generating a lot of heat. So this is megawatts, 10 megawatts, 20 megawatts. So during this period when you disconnect power, they still have UPS, so we call this battery, which allows to IT infrastructure to operate. But the cooling system has discontinuity of operation for between few to maybe 30 seconds before, you know, power comes back to online. And during this time, unit stops, but heat is still produced by data center. And so the discussion here is to say that, you know, depending how quickly your chiller can restart and come back to 100%, will reduce the stress on your data center in terms of increase of temperature inside IT space. So we have made this test, this time extremely short. In this presentation, I'm showing 1 minute is between 1 and 2 minutes. It means that when power comes back, in less than 2 minutes, you have 100% of capacity available for data center, which is very quick, and it helps to reduce, you know, storage tanks and you name it in data center. So this function is very important for our customer. There is all series of different type of power connections. Some of customer wants to have one power connection, some wants to have two power connections, you know, separated for pumps, separated for controls. We can adapt to all this kind of requirements. I forgot to say about controls that controls also has a backup battery. We call this, you know, ultra capacitor. So that which means that during this power transition, unit control is still alive. So it means it's a kind of doesn't need to reboot, you know, this controller, which means that we can react very quickly as soon as power is back to restart compressor in the correct mode. Then few elements on heat transfer. I think that we don't talk enough about heat transfer. Heat transfer and compression is the main elements of our systems. We were the first to introduce microchannel heat exchangers. It was, you know, probably 2006, 2007. Today it has become a standard. We also have now introduced hydronic coils for free cooling. So this is important for us. We manage this, we master this technology. We know very well how it works, and we are kind of leader in this technology. And then I will have specific slides about free cooling option. Free cooling is integrated. You probably have some idea about how it works, but basically this is additional heat exchanger, hydronic heat exchanger, which are up front of condenser coils, so they are in series. I don't have specific slides about compressor, but this is latest generation 100% free cooling, 100% variable speed drive compressors. So we don't have slide valves anymore in this compressor. This compressor has been designed with the latest technology, very high efficiency, but it uses only variable speed drive to adjust to capacity required. It has also a kind of integrated automatic VI adjustment. You know, in compression world, it's a ratio between discharge and suction volume. I will not talk about this, but this option is included in this compressor, which makes adaptability of this compressor to condition and to load very unique. And then very important, I will have specific slide about this, you know, how we are arranging evaporators. It's not about how we put them together, but also how it's designed. You know, in data center, usually customer likes to work with constant delta T across evaporator. So let's call this 30-20, entering water 30 degrees C, leaving and 20. Whatever load of a data center can be. So it's 100% of flow. But if you are going, you know, to 30 or 25% of load, your water flow should be 25 or 30% of the full load if you want to maintain the same temperature differential. And it's a little bit of challenge for a lot of heat exchanger design, because, you know, when you reduce too much water flow, you can be in the laminar flow, and you know that the heat transfer is reduced drastically. We have a special inserts inside the tubes, and this is a very important feature, which makes operation of our evaporator possible with very, very low flow, which means that we can go from 100% to 15, maybe 17% of capacity with constant delta T with very, very limited flow. And this is relatively unique. So it makes hydronic installation very easy. You don't need to have any recycling pump. We are also can benefit, you know, from minimum energy consumption due to the reduction of the flow. You don't need to maintain relatively high flow, and it reduces also benefits of free cooling. I will probably talk later about this. So this is very, in one slide, some of the options. I'm not talking here about integrated hydronic options. Of course, we have, you know, hydronic pumps, different size. We can manage, you know, as much as 300 kilopascal available static pressure. So it can be primary, it can be secondary pump, already included in the chillers. Okay. Very important elements, you know, in our chiller design. I will not make overview of entire product lines, but generally speaking, for the larger capacity. So if you go above, let's call this 700, 600 kilowatts, we systematically have two modules of the unit side by side. It looks like one machine, but actually it's two independent modules with two independent evaporators. And this is a very important point, because what happens, water enters to the first evaporators and then in series go to the second one, and the final cooling is provided by the second evaporator. So it seems to be a kind of obvious. It's not, because there is very significant difference of putting two evaporators in series or putting them in parallel. So if you put them in series, then you have the first evaporator, which will benefit from higher living water temperature than, you know, the final one. And you probably know that higher living water temperature you may have in your system, higher efficiency system will have. So we, by putting the units in series in this specific way, we can benefit in this upstream unit of about, you know, 5-6% efficiency improvement without doing, you know, any improvement on compressor, heat transfer, etc. So this is purely system architecture. And this is something which is very important. Excuse me. It's very important not only for this specific chiller. This is something we have developed, you know, in my previous life for district heating application, mainly speaking, and eventually connection between data center and district heating. So I will try to do a little bit of thermodynamics here just for 1 second. And I'm talking here about generic case of unit installed in series versus unit installed in parallels from water perspective. And as an example, I'm talking here about water-cooled systems, but it applies to air-cooled system as well. So without entering too much into details, everybody knows parallel type of configuration. So the same living water temperature is seen by each of the unit, operating in the group. You can have 2, 3, 4, 5 units. So each of them, they see the same entering and the same living temperature in both evaporator side and condenser side. If you try to represent what happens inside this kind of system, and I'm simplifying here by using Carnot cycle, so it's a kind of ideal cycle, which our refrigeration cycle tries to be as close as possible. So it's not 100% representative to what we are doing in air conditioning, cooling, and all type of thermodynamic machine, but it's close enough to analyze, directionally how things behave. So generally speaking, if you look on the TS and you see here in the top entering and leaving condenser water temperature, I'm simplifying without adding additional pinch in evaporator and condenser, etc. But generally speaking, you have in this diagram water enters in one side and leaves in a higher temperature in condenser, and evaporator opposite happens, enters at higher temperature, leaves in lower temperature. And your refrigerant temperature will be just above in condenser, above living water temperature, and in the evaporator below living water temperature. So it represents a cycle. And if you represent this in TS diagram, the green area inside this square represents input power. The blue one represents cooling capacity, and red represents heating. So basically, if you think about COP, it's basically the blue divided by green area. Okay, so this is traditional parallel application, and whether you have 1, 2, 3, or 4, because they will see exactly the same condition entering and leaving evaporator, they will have the same thermodynamic cycle, so they will have the same efficiency. Okay, now it's interesting to see what happens if we put the unit in series, maybe parallel. In this particular, it's counterflow. What happens, in a TS diagram? Well, as temperature, it's not the same for each evaporator and condenser for each of the machine. The cycle becomes a little bit funny, because you will see the machine which sees the lowest living water temperature. Let's say that this is this one. It will have also the lowest condensing temperature. So it's here. So basically, it will have smaller green area, which represents input power, than equivalent, in the top view. So if you continue like this, you will see that basically all this area in the top and this in the bottom is the potential energy savings, input power energy savings, due to serial configuration. So now, if in the top you have air-cooled machine, this will be straight, so you will not gain much. It will have only the part of the savings in the bottom. If you have water to water, if you can afford to put both of them in series configuration, you can by nature have much higher efficiency than putting machines in series. Of course, there is a lot of constraints, and it works only if gradient of temperature, so it means difference between entering and leaving, is large enough that this area becomes significant. And just for your information, data center is the case. In data center, usually we are operating with 10 degrees C or sometimes 12 degrees C difference. So this is just a parenthesis. I'm showing here why we have done this. And before I go to the next one, I just give you example of savings, and I'm giving you here a magic formula. We call this Michel Grabon's formula. I derived this, a few years ago, which very easily allows you in the Carnot cycle. So you can say, yeah, probably in the real world, I will have 80% of this. What is the efficiency gain? Giving temperature differential in water, in evaporator and condenser side. So larger temperature differential you have, so it means this temperature gradient, larger gain you have, because this is proportional. And you see that if one of them, there is no differential because, there is low delta T, then, you can neglect this. Very important terms is this one, and you see this is the number of machine you will put in series versus parallel. So you can very easily check that if n equals 1, if you have one machine, this becomes 0, so there is no efficiency gain. So at least this formula is homogenic. And you see that if n goes through infinity, it's a kind of has tendency to be asymptotic, which makes sense because you cannot gain more than triangle you have here. And I gave here example. This is for district heating. If you have temperature differential in both sides 15 degrees C, so imagine 15 degrees C differential in evaporator, 15 temperature differential in condenser, which is dependent on customer application and some other constraints, so it's not always possible. And in this particular case, difference between high, so let's call this condensing temperature and evaporating temperature around 50 degrees C. This curve shows you what is the efficiency gain versus pure parallel operation just by putting the unit in series. And you will see that with 3 units, you can have like 20% gain. So this is in ideal situation. In real world, maybe 15, maybe 16. But to gain 15, 16%, it's a big challenge, without doing, revolution. And frankly speaking, chiller words, I don't know how you can improve efficiency of the chiller by 15% when your isentropic efficiency of compressor is about 80. And efficiency and pinch of your heat exchanger is around, 0.5. So basically, this is the only way to have significant energy savings in application is by putting machines in series, when it's applicable. So this is what we have done in our application, in free cooling chillers. Now I will accelerate a little bit, so I will not enter to each of the details of the design. But basically, natively, this machine has been designed to provide free cooling. So it means, I will show this slide. We have basically 2 types of free cooling application. So we have one application we call this standard, or in European context we call this glycol solution. So generally speaking, you imagine from data center or from the customer, water arrives at certain temperature, let's say 20 degrees C, and will leave at 30 degrees C, will leave at 20. If there is no opportunity to do free cooling because ambient temperature is high, then we are going directly through evaporator, and you have, traditional compression-based Rankine cycle, which will provide you the cooling. So this valve is closed, this one is open. This is just straight cooling chiller. But if there is opportunity of free cooling, so as soon as ambient temperature is below leaving return water temperature, so imagine if return water temperature is 30 degrees C and ambient temperature is 25, even if you want to produce 20 degrees C in the end of the process, you can start to pre-cool your water with those hydronic coils, and then continue the cooling with mechanical cooling if needed. So basically, we call this glycol solution because usually this fluid will be glycol. Why? Because during winter time, we don't want to freeze basically water in the coils. So we need to protect the coils, and because it is the same flow going through the coils and used in the system, we have to have glycol everywhere if you want to have a glycol in the coils. Then we have another option, we call this glycol free. So this is an option in which customer wants to use water in the main loop, and in this case we are adding additional heat exchanger with small pump, and then we have only glycol in hydronic free cooling section of the unit. And main flow is water coming from the customer. And basically, if we have free cooling operation, we close this valve, water is going through this heat exchanger and then through evaporators, and this heat exchanger is providing free cooling by application of pump here and free cooling operation. So it basically makes the system independent in terms of fluid between what is in the main circuit and hydronic free cooling circuit. However, you have additional heat exchanger, which makes it a little bit less efficient. And and in this particular option, the question, what should be the speed of this pump versus flow and load, is the question of optimization. So we have made this pump variable speed, and we have realized by smart optimization of the speed of this valve, we can benefit of much higher efficiency than in traditional. But this is just an element of our optimization. So this is the actually what you call PID of the system. So you can see it's a little bit complicated. So you have, the two system. I said that starting from 700 kilowatts, we have two machines connected together, which makes, larger system. They have two pumps, compressors, evaporators, hydronic coils, etc. And because we have those two machines in series, in mechanical cooling operation, we benefit to 6% of efficiency improvement versus operation in parallel. So this is this percentage, which I was saying is for free when you put the unit in series smart way. So generally speaking, I will just very quickly go with you through how water flows. So I have put some arrows here. So water enters and goes for two modules. Each of the modules, by the way, has its pump, which basically operate in parallel. So if you are following the green part, so this is in the case what we call mechanical cooling. So there is no opportunity for free cooling. So they join together in this point and then enters to the first evaporator, second evaporator, and leave the machine. So, customer doesn't need to know all the details, how it flows inside, but from you engineers, it's important to know. Basically, in mechanical cooling operation, the only interesting thing to know is that we are operating evaporator in series. So if it enters at 30 degrees C and is supposed to leave at 20, we will probably have something like 25 in the middle. So it enters in two pumps, then enters to the common line, first evaporator, second, and leaves. Okay, and compressors, economiser, etc. works traditional way. If you are, I'm not sure if I can. No, it works. Sorry. Yeah, when we are in, so it was mechanical mode. In the free cooling mode, basically water enters, in both sides is the same. And this valve is closed. This one is open. So water first will go through hydronic coils, which will benefit to lower ambient temperature, then, water return, and then will come back to this point. And then if needed, additional cooling will be made. So it means that by playing with those two valves, we can send water to hydronic coils or directly to evaporator, and always water afterwards go through the heat exchanger. So if additional cooling is needed, it will be provided by compressor, one or two. So because in some modes, if only very, very small amount of additional cooling is needed, this compressor may be closed, and the only capacity from mechanical part will be provided by this. Okay, now we have the notion of free cooling operating envelope. It's a kind of function of leaving water or entering water temperature, what customer will have, and ambient temperature. So you can understand if ambient temperature is low and water is hot, we have much more of free cooling opportunity. If leaving water temperature is low and ambient temperature is high, we have mechanical mode. So all the question is to know through the year of operation and through the year loads, how much of unit will operate in total cooling, free cooling, on mixed mode or mechanical, and you understand that free cooling mode has much higher efficiency than mixed mode or mechanical mode. Okay. So what I have done these studies for several cities in your beautiful country: Brisbane, Sydney, Melbourne, Adelaide, and Perth. And I was using some kind of data, so you can spend hours discussing. So it was metronome data. I can do this, with AIRAH or some other. I had much better access to those data. And why I'm doing this, we understand that free cooling efficiency or impact is the function of ambient temperature. So it will not be the same impact if you are in Brisbane or Sydney, or it will be not the same efficiency during day and night. Okay. So you cannot say this machine free cooling has such and such efficiency or will consume such and such amount of energy without saying when it will be installed and what will be the water temperature or what will be the load. Okay, so those loads elements, as I have shown here. So depending on the load and temperature, you may have different results in terms of efficiency. So we took 8,760 hours, so entire year data, and they are like they are. So you see, some variation. It's colder during night, hotter during the day, and it's hotter in your particular countries in January, in December, than in July and August. So there is some kind of patterns. So it needs to be analyzed one by one for each specific location. So I took, for instance, but if you take Sydney, for instance, so if you look on those data, it's a little bit hectic. But if you if you treat this, if you sort them, you will see that there is a distribution of temperature. We call this bins, and you will see that in Sydney there is very few temperature above 35. There is almost no below 5, and the average is somewhere here. So this is number of hours. So you will see that you will have at temperature 20. There is exactly 600 hours in Sydney when temperature is 20 degrees C, and there is probably 300 hours when temperature is 10 degrees. But if you take average 17.9. So now, if your data center water temperature is 30-20, it means in average you can do significant amount of cooling because you can go from 30 to 20. You will have enough free cooling. I did also another kind of sorting of those data. So it's a kind of integration of this curve. And basically how you read this, if you put the pointer in this curve and you look left, it will tell you how many hours temperature is below certain level. So in other terms, if you take 30 in Sydney, you will see that 100% of time temperature is below 30, almost, so it was a surprise for me. If you take 15, you will say, okay, 15, I will have about 40% of time temperature is below 15. What I'm saying is, it gives you idea about what is percentage of time I can access or I will operate in free cooling. So for instance, if we start to activate free cooling at 25 degrees C, you will see that in Sydney, almost 90% of time, you will be activating free cooling mode. Okay, so this is very interesting. And I did this for other places. Perth, different distribution, different set. But in Perth, if you are looking at 25, only 80% of time you have a chance to activate free cooling if your water temperature is 30-20. In Melbourne, 85% of time. In Brisbane, only 75, so it's hotter, but still, significant. So it's not like Adelaide, 90%. It's not like, hot countries like Australia, image we have, no potential for free cooling. If you start to have high temperature water loops, which is the case for data center application, it's not the case for air conditioning, then you may have, a significant amount of free cooling. Then I will have few slides. I will go probably quickly to leave you some time for question if you have. But basically, there is another question which you have: what is my temperature distribution? The question also comes: what is my load distribution? Okay, so in other terms, data center, you can say, it's always loaded. Okay, what does it mean always loaded? So you can say, let's see what happens if I have constant load across the year, 100% of load. For instance, if it's 1800, so 1800 across the year, it may be 75% load, 50 and 30. Usually people are asking, give me, data for 100% of load across the year. What will be the PUE or average efficiency, or 75 or 50? But you can see that in a lot of data center, they have a kind of variability, like for instance, banking, some video streams. People have tendency to use it more, in evening than during the day, and there is some kind of patterns which can be, represented in sinusoidal form. So you can have like 24-hour variation and a weekly variation. If you add them together, you will have a strange variable load patterns. You can, of course, receive also data from customer and say, okay, customer, this is your pattern of your load through the year, this is the location. We can calculate what should be your energy consumption with and without free cooling. Okay, so this is what I'm trying to see. It's to tell you, you know, for all of those locations we had look on, if I have constant load or if I have variable load, what will be impact of having data center equipped with or without free cooling. Okay, so I have a little bit of details about, you know, how we calculate PUE and also practically speaking, how do we do simulation of PUE? So in some terms, you know, we are not always calculating 8,760 hours, so 8,760 specific operating point, temperature and load, which can be by nature variable. So we're kind of clustering the data, etc. So I skip this one because I think that we are a little bit short on time. And this is PUE calculation as well. And I'm giving to you directly results. So the question was, if I have my data center carrier chiller 30XF, by the way, we have option of the same chiller without free cooling. So we can talk about operation with free cooling or without free cooling. So the first thing which is interesting to see, and as I said, we can have different type of load. So I have applied a kind of specific load, but I have compared also constant load to variable speed load. So imagine if my annual load variation was like this, a kind of 1800 max and probably around 20% variation, average 80% load, but with some variation. What is the amount of capacity which will be provided by free cooling dependent on location? So I'm talking about energy which was rejected to the air without operating compressor. So we see that this is in Sydney 50%, 40% in Brisbane, 65% in Melbourne, 49% in Perth, and 55.8% Adelaide. It's function of temperature for sure. And then I have calculated, you know, standard means without free cooling and FC means free cooling operation. So you see operating for different location. I'm calculating what is EER, so efficiency from the chiller perspective, and PUE is this power utility effectiveness, more the value which is used by our friends from data center. So here higher is better and here lower is better. Okay, so the good PUE it's, you know, around 1.2, not so good is 1.4. But to make story short, I see positive impact on free cooling operation. We know that if you have this free cooling coils, it will generate additional pressure drop in the air side, so it will increase slightly fan consumption. So in some cases, you may argue that probably what I will win in free cooling side, I will lose in mechanical cooling. It's not the case if you do this calculation in details. And what I have done also, I have calculated what will be savings for 1 year of operation with this 1800 kilowatt loads, with the cost of energy about 10 cents kilowatt hours for different location. And this is probably something which is the most important. You will see that in 1 year of operation, 80% loaded data center in the context of Sydney, Brisbane, Melbourne, Perth, and Adelaide will give you energy savings between 65 and 87,000 dollars a year. Okay, so it's significant savings. I did also very short comparison between if I'm doing with and without this variable speed load versus constant load. So variable load was the one I was proposing and constant load. So you see here the numbers, but generally speaking, if you compare 1.6, it's about taking 75% load corresponds to what I have done. So there is no big discrepancy between using constant and variable speed approach. Just basically what I'm saying here is that we can adapt if needed to whatever load patterns you can have, and we can make accurate calculation for a data center customer. This is, by the way, very often what they are looking for. Important element is what is temperatures, what is the load, what is the water temperature, and what is the air side temperature to calculate those values. But my conclusion here, even in the Australia context, free cooling application is actually very, very promising one. And I will very quickly go just to one or two slides just to say that CARIAH is not only chillers. We have, broad portfolio of product which can be applied in data center. I concentrate today in climate controls, so the chiller side, but just wanted to tell you very, very important that we have very sophisticated and well-perceived offering in what we call system level controls, or BMS. We call this ALC, which is a part of our corporation. And they are very successful in data center space, particularly in the United States. And very importantly, we do have acquired, 2 years ago, the company which name is Enlight, which does what we call data center infrastructure management, DCIM software, basically, which means to, manage all infrastructure, physical infrastructure, computers and other stuff, you can have in data center. And this DCIM starts to be successful in Australia, and my colleagues from Enlight actually had a series of conferences and meetings a few weeks ago in Australia, so you may have met him. And what I wanted to say, just my last slide, that going forward, we see a lot of opportunity of connecting DCIM, which has information directly from data center, ALC controls, and thermal, which means chillers and air handling units. If we take into consideration, given load, weather data, and IT load, we can optimize all set points in data center and actually reduce operational cost of data center by smart management of set point, which today is not always the case. We have now all element on hand. We are working on this. We don't have product yet, but maybe for the next talk, 6 months from now, I will be able to present you very exciting project. And I think this is all I have for today.
We do have a question that has come through in the Q&A, so I'll just read that one out. The question is, can you please confirm if we have the high static condenser fan option available with this product?
It depends. It depends what you call high. We even in 50 hertz operation, which is the case in power supply in Australia, we do have as an option 60 hertz. We call them 60 hertz fans. So we can overdrive fan to run at 1145 pascals. So we can, I don't have number now in my head, but we very frequently we are installing sound packages around the chillers, because very often in these crowded cities, because of neighborhood, etc., sound levels are a major concern. Generally speaking, they have between 15 and 50 pascals pressure drop, but sometimes there are some additional louvers. We can go up to 85 to 95 without any problems. If it's higher, we need to check. But yes, we do have it.
That's great. Thank you. Just while we're waiting for other questions to come through, people, please feel free to type them into the Q&A box as well. And we can start going through those. I know we've got other CARIAH members on the call as well. So if anyone has anything, please, now is your time. Damita, hello.
Yeah, hi, I'm Damita. So look, if you guys have any questions regarding this product or the application or the Enlight, please feel free to reach out to CARIAH colleagues in any of the offices. We'll be able to provide you additional information or do a follow-up presentation as well. But still, I think we have a little bit more time. If anybody want to ask a question, type it in the Q&A session. Thank you.
Thanks, Damita. A question that's coming through now is from Peter, who's asking, is adiabatic operation possible with these chillers?
Sorry, I don't.
Adiabatic operation. Adiabatic.
Yes.
Yeah, we do have this option. We are not installing them in the factories as of today, But a lot of distribution centers, like my friends in Australia, they do have local partners. We do this, in Middle East. We do this in Switzerland, and it's possible option. Having said this, we see less and less adiabatic application in Europe. That's why we have not created integrated option yet, because there's more and more concern about water consumption and water usage and cleaning, etc., etc. But still, it's still possible option.
Yeah, that's correct. We can supply locally the adiabatic option. And there is another question, Michel. What's the fan pressure drop, through the additional hydronic condenser coil?
Yeah, it's about, I just need to think, it's about 5 millimeters, okay? So it depends on speed. All fans are variable speed, by the way, but at full load, 60 hertz, we are running 6 cubic meter per second per fan. And in this operating condition, I think we have about 5 millimeters pressure drop, so 50 pascals in condenser, about 5 in hydronic, so it makes it 100, and we have additional 100 available, for system level pressure drop and etc. So we can go up to 200. Yeah.
And meanwhile, there is another question. Has there been any installed any of these chillers in data centers in Australia?
I don't think yet. We are working on several projects. We are supporting our colleagues, but I don't think we have sold in Australia yet.
Not yet. We participated in some tenders, not yet finalized. So, and also this product is finally getting released also.
Yeah, it's like, it's a little bit complicated, but it's really new. We have, as we speak now, we have about 100 units operating, an additional 100 delivered, but not started yet. And we have a very, very deep, very, very big success in the market, because it's a really product for data center, and we are gaining more and more confidence from the market side. So we have a couple of very, very big customers which actually has decided to work with us as preferred supplier. But now we are, and so in the beginning we concentrated, in few large customer in European market. Now we are opening broadly. Australia for me is the next targeted market because of its sophistication and technical level of the people living there. So I think that it helps. But we will go across the globe. Product will be produced also in China, in the US. So today it's produced in Europe, but starting from January we will produce them in Shanghai, and the next year also in Charlotte. So it will be really global product. And what I wanted to say, that we have now very sophisticated simulation tools. So I know that technical community usually asking for question, and we usually suppliers has tendency, to take time or to have some problems to generate good, reliable technical data. Now we can support you very easily. So if you have, if you want us to generate tables in the different loads, different ambient condition, PU calculations, free cooling, no free cooling, limited input power, all type of question with data center customer are asking, please send them, to our colleagues in Australia, and now we are able to support you globally for this kind of questions.
Thanks, Michel. Another question is there, because the chiller fans, encounter the resistance with the free cooling coils all the time during free cooling mode and without free cooling mode. So is the energy saving by free cooling is higher than the fan's additional energy consumption, or it depends on the weather?
Yeah, this is exactly idea. And by the way, if you were, you see this here. So we have this with and without. So when I'm saying without free cooling, it's not I'm just deactivating free cooling option, I'm removing free cooling coil. So here, standard operation, like for instance, this one here, if you take Sydney, if I were operating in Sydney, optimize, this is a very, very good chiller, by the way. Without free cooling, my annual efficiency will be 6.63 and PUE 1.29 with my assumption. Now, if I'm adding hydronic coils, additional pressure drop, so I'm penalizing my operation, in the mechanical mode. But what I gain in free cooling is more than I'm losing in mechanical mode. So you see here the numbers: 10.72 EER, 122 PUE, and this is just take the unit, connect, water, it's done. So this is what I'm saying, that this is not like you need adiabatic cooling, you need bypasses in water side. It's package chiller with water in, water out. Everything is inside, and this is a level of improvement you may have. I have done exactly the same studies 10 years ago for air conditioning application, and opposite has happened. So I refused to develop free cooling option for hydronic coils, because actually we were losing more in the air side due to the pressure drop than we were gaining on free cooling operation. And this is very simply due to water temperature. When you operate with 10 degrees C or 12 degrees C water, you look on your charts relative to the temperatures. If you look at 12 degrees C water, you will have maybe 25-30% of time when you can get some free cooling, and particularly it happens in the time when air conditioning is not necessary. So there is no much of gain. Data center is completely different story. You have loads, and you have much higher living water temperature.
Yeah. Thanks, Michel. And another question: what is the current lead time for these chillers?
So the standard lead time will be 18 weeks. Okay, so it's between 16 and 18 weeks. But we have so busy factory now because of success that if you purchase today, it will be difficult to have delivery before November, December timeframe. So it's reduced. If you think about 2024, standard lead time will be 18 weeks, 16 to 18, and then you have the transportation time, which is probably additional 4 to go to Australia.
Yeah. And another question is there a tool to compare the savings, using data center dedicated chiller or versus a standard chiller?
So I'm using the tool which you have. It's not the tool which we are giving outside, but our sales force eventually will have access to the tool. Everybody today, it's limited to few experts per region. I'm not sure, Damita, if you have formed somebody in Australia, but we have formed a couple of folks, in India. So if needed, we can probably add the 1 or 2 persons.
Yeah, I think we can organize the one for Australia as well. Yeah, thank you. I think no more questions. We are on time.
I think that's all.
I think that
unless you have anything else to add, Michel, or
no, just one comment. Just I wanted to thank you to give me this opportunity to talk about technology and about data center sustainability. I think Australia is one of the leading countries, going green, and I think that you need to consider this kind of solution, to your data centers. Okay. Thank you very much.
Thank
you very much. Thanks.
No, that's okay. Just want to say thank you as well to everyone who attended today's session. As always, the recording will become available in the next 2 to 3 weeks. The recording should be made available, and I'll send you out an email when that does become available for viewing. Thank you to the team at Carrier. Thank you, Michel, for the presentation. If you do have any questions or any follow-up questions, feel free to get in touch with me. And I can send your questions on to the team as well. So thank you all once again. If you want to register for any of AIRAH's other upcoming webinar sessions, technology talks or streamlines, you can view a list of those on the AIRAH website. So thank you all once again, and until next time, take care.
Thank you.
Thank you, Mary.
Thanks. Bye.